I have an integral that I really don't want to do that badly. I would like to find some other tool than doing it by hand. If you look at the answer down here, this is how the Q equals is what happens if you actually do integrate it by hand or get Wolfram Alpha to help you out doing the integration. So what we're going to try to do is not start at that top part, not do the integration by hand, but still somehow get this value down here, this 2.39 joules per second. That is the actual property of this particular fin, the fin we've got some parameters for. If we include those parameters, we're going to get a nice value of how fast heat is radiated out per second, energy is radiated out per second. But the main thing is, we need to do an integral. The integral is hard, the kind of thing you might not be able to or might not want to do by hand. And we want a specific numerical value out, so it's a definite integral. We want to find a way to get MATLAB to help us do that integration. We're talking about antiderivatives integration, and what I would like to emphasize, as I did with equation solving, is if you can integrate, if you can actually find antiderivatives, you get exact values. That's good. We like exact values. We can reuse results. If we can get a general form integral, hey, I can use that formula for the next problem, the next problem, the next problem. If I have different kinds of fins, I can instantly reuse the formula. That's a good thing. The downside is the computing side. If you have a function like e to the negative x squared, there is no formula for that. There's no closed form integral for the bell curve, which has caused no end of grief over the years. So that's one thing you might encounter. You also might forget how to do the antiderivative. For example, if you had this horrible mess that we had here, sorry, back two more. If you had this, you might go, I'm not really sure I'm prepared to find an antiderivative of that. Fair enough, that happens sometimes, more frequently than you might expect. Sometimes we actually don't have a formula. Like if we have f of x equals x squared, that's fine. But we might be measuring something. And if we're measuring something, then we don't have a formula. I can't do an antiderivative by adding 1 to the power, dividing by the new power. So we're going to need something else for that. That'll be what we handle last in this week. But there are a bunch of scenarios where there is no way to get this nice exact antiderivative that can be reused for other applications. Sometimes we fall into these other camps where we've got to do the integration by a computer. We're approximating. We're settling, but we're settling hopefully for a good reason. Something we actually can't handle any other way. Phrasing-wise, the word quadrature I'm going to introduce here. It's not something that people use as often these days, but you'll see it if you are looking for integration techniques. Quadrature is the same thing as integration. And the reason, or the source of it, is it comes from quad, square, squaring the circle. So back in the Greek times, one of the challenges was to use a compass and a ruler to somehow find the area of a circle, which of course was really hard because you had to somehow turn a circle which has something with a pi in it into something square. And when you have irrational numbers running around like that, it turns out to be actually impossible to do with compasses and rulers. But it was a challenge that they set up, and it led to the kind of numerical integration that we do today. So if you think quadrature, think numerical integration. We're going to do a couple different cases. For today, we're going to focus on the case where we have a formula. So this case, we have a formula for what we want to integrate, and we're going to focus on that. So here's what we're doing in a more practical or graphical sense. Here's what I want to integrate. The convection times p times t of x. But as soon as I say integral, and I graph, this is the graph of f of x, which is equal to h times p times temperature, so a couple of constant times temperature. The integral is equal to what part of this graph? Area, exactly. This area is what we want to find. So what we're going to do is go straight back to what you saw in first year. Hey, integrals and areas, those are related. So why don't we think about how we could estimate that area using some other shapes? Again, the problem here is that this is a curved graph. We don't know how to find the area underneath that, or maybe we forgot, or maybe it's too hard. We don't know how to work with it right now, though. So let's go back and get the computer to do some heavy lifting for us and estimate that area by subdividing it. What we're going to do here is subdivide into little panels. And on each panel, we're going to be able to estimate the area pretty well. And if we do that for a bunch of panels, then we're going to get a pretty good estimate for the area overall. So exactly what we saw in introducing integration, now we're going to go backwards. We know there's a good way by antiderivatives, but maybe that's not available to us, so we're going to go back and say, well, where did this come from as an area calculation?